Well, I think that there's increasingly a convergence actually between SpaceX and Tesla and XAI. It's going to be, I think, if you can think of it, you can have it, will be the future. Then I would say that's probably a good company to invest in. When Tesla is doing simulations for self-driving.
For most of the last decade, when people argued about the future of the automobile, they argued about batteries. Range, charging speed, price per kilowatt hour. That was the conversation everyone assumed would decide the winner of the electric car race. Almost nobody was talking about the motor. Motors were considered a solved problem, a mature piece of engineering that nobody expected to change the game. Then, a handful of teardown engineers got their hands on Tesla's latest drive unit, cracked it open on a workbench, and realized they were looking at something that didn't belong in a mainstream production car at all. What they found inside reset expectations for what an electric motor could do. And it did it so quietly that most of the industry didn't notice until it was already too late to catch up. To understand why this matters, you have to go back to the assumption every car company built its electric strategy around. That speed and efficiency were opposites. Push a motor hard enough to deliver blistering acceleration, and it gets hot, heavy, and thirsty. Tune it for range and efficiency, and the car goes soft, losing the instant punch that made electric vehicles exciting in the first place. For years, this wasn't treated as a limitation to be solved. It was treated as a law of nature, something you designed around rather than something you fought. Entire engineering teams built their careers optimizing around that ceiling instead of questioning whether it was really there. Tesla's engineers apparently didn't get that memo, or more likely, they got it and decided to ignore it. Somewhere inside one of the company's development labs, a small team was handed a brief that sounded almost impossible. Build a motor cheap enough to put into millions of ordinary cars, while pushing performance and efficiency further than anything the industry had produced before. What came out of that lab broke the compromise everyone else had accepted as permanent. The heart of the innovation is deceptively simple to describe and brutally hard to execute. A carbon fiber-wrapped rotor. Inside any electric motor, the rotor is the spinning heart of the whole system, and at high speeds it wants to tear itself apart. Centrifugal force pulls at every gram of material, and conventional rotors simply cannot survive extreme rotational speeds without flying apart or warping under stress. That's why most electric motors on the road today are capped well below the RPM levels, where the real efficiency and power gains live. Engineers hit a wall imposed by the physical strength of the materials they were using, and they stopped there. Tesla's answer was to wrap the rotor in a shell of carbon fiber, a material prized in aerospace and motorsport for offering enormous strength without adding meaningful weight. That wrap acts almost like a cage, holding the rotor together under stress that would shred a conventional design. With that structural problem solved, the rotor could safely spin at speeds that would have destroyed earlier designs, reportedly well beyond 20,000 revolutions per minute, a number that used to belong exclusively to specialized racing or aerospace hardware, not to a family sedan idling in a school pickup line. But raw rotational speed isn't really the headline here. What actually matters is what happens once you can spin a rotor that fast without it shaking itself apart. The whole system becomes dramatically more stable, vibration drops, and more of the electrical energy pulled from the battery converts directly into forward motion instead of leaking away as waste heat. In a conventional motor, a meaningful chunk of every charge is lost this way, turned into heat that then has to be pumped out by heavy, expensive cooling hardware. Tesla's design claws a large share of that lost energy back. The result isn't just a faster motor. It's a motor that goes further on the same battery pack, while also hitting harder off the line, which is precisely the combination the entire industry had spent years insisting was impossible. This isn't a hypothetical improvement sitting in a lab. It already showed up in the real world in cars like the Model S Plaid, which pairs multiple versions of this kind of high-speed motor to produce over 1,000 horsepower and a 0 to 60 time that. Lands under 2 seconds, territory that used to belong exclusively to 7-figure hypercars, not 5-seat family sedans with usable trunks and hundreds of miles of range. That's the uncomfortable proof point for every competitor. The trade-off they'd built their entire product strategy around apparently didn't have to be a trade-off at all. Here's the part that should worry rivals even more than the performance numbers. This technology is agonizingly difficult to copy at scale. Wrapping a rotor in carbon fiber sounds like a straightforward manufacturing step until you actually try to do it. The fiber has to be wound onto the rotor under exact, unwavering tension. Too loose, and the rotor flexes and fails under load. Too tight, and the fibers themselves crack. Then the whole assembly has to be cured under precise heat and pressure, and every finished unit needs to be balanced to a tolerance that most factories have never had to consider, because an imbalance that would be invisible at normal highway speeds turns into a violent, self-destructing vibration once you're spinning past 20,000 RPM. Tesla reportedly had to design and build entirely new manufacturing equipment just to produce these rotors reliably and at volume. Machinery that didn't previously exist because nobody else had needed it. That's the kind of institutional knowledge you can't simply reverse engineer from a teardown video. A rival company can buy one of these motors, take it apart, measure every dimension, and still be years away from being able to replicate it at the scale and cost Tesla is targeting. Because the real breakthrough isn't the concept, it's the accumulated, expensive, failure-riddled process of learning how to build it perfectly, over and over, without bleeding money on scrap parts. Some industry analysts have suggested competitors could need the better part of a decade to close that gap, and by the time they do, Tesla will likely have already moved the target again. And moving the target again is very much the plan. Tesla has reportedly set an internal goal of bringing the entire cost of a next-generation drive unit, motor, gearbox, and power electronics combined, down to somewhere around $1,000 to produce. For context, some competitors are believed to be spending 3 to 5 times that figure just to achieve comparable performance. That gap doesn't stay small. Multiply a few $1,000s of difference across hundreds of thousands of vehicles a year, and you get a margin advantage large enough to fund entire new product lines, while rivals are still trying to break even on their electric vehicle divisions. Tesla isn't stopping at the rotor, either. The company has also been working to reduce its dependence on rare earth elements like neodymium and dysprosium, materials that sit at the core of most high-performance electric motor magnets, and whose global supply is concentrated in a handful of countries. That concentration has been a quiet but serious vulnerability for the entire industry. Prices and availability can shift overnight based on a single trade policy decision thousands of miles away. A motor design that needs meaningfully less of that material isn't just cheaper to build. It's less exposed to a supply chain that no single automaker actually controls. Alongside that, Tesla has been redesigning its power electronics to rely less heavily on costly silicon carbide semiconductors, chasing lower costs and fewer external dependencies on that front as well. Put those pieces together and a pattern emerges. Lower production costs let Tesla lower prices. Lower prices attract more buyers. More buyers mean higher production volume. Higher volume builds manufacturing experience faster, which drives costs down even further, and the cycle keeps compounding on itself. Meanwhile, most of the traditional automotive giants, companies with a century of manufacturing experience behind them, have struggled to make their electric vehicle divisions profitable at all, even while producing genuinely well-reviewed cars. Building an impressive prototype is one challenge. Producing millions of reliable, affordable units at a profit is an entirely different and much harder problem. And it's a problem that has quietly humbled nearly every legacy manufacturer that has tried to compete in this space. There's a reason Tesla was willing to push this technology out into the world right now, and it isn't purely about engineering pride. The Cybertruck, once positioned as the flagship proof of Tesla's ability to reshape an entire vehicle category, has underperformed the sales expectations that were set for it. Reports have suggested that a significant share of registrations in some quarters came from Tesla-affiliated entities rather than independent buyers, and recalls have chipped away further at public confidence in the product. For a company whose brand identity is built on the idea that everything it touches redefines its category, a stumble like that carries weight beyond the balance sheet. It creates pressure to deliver something that can't be argued with, not a styling exercise or a marketing campaign, but a genuine technical leap that changes what the entire industry considers possible. The drive unit appears to be exactly that kind of answer. It's worth stepping back and noticing that this motor doesn't exist in isolation. It's one piece of a much larger, self-reinforcing system Tesla has spent years building. Cheaper, more efficient motors mean Tesla can build and sell more cars at competitive prices. More cars on the road mean more real-world driving data flowing back to the company, which feeds directly into the development of its self-driving software. Better software makes every Tesla more valuable to its owner, which supports demand for the next generation of vehicles, which funds the next round of engineering investment, including the next version of this same motor technology. None of these pieces exist by accident. The company has also invested heavily in its own battery cell production, its own charging network, and its own computing infrastructure for training its driving software, reducing its reliance on outside suppliers at nearly every stage of the process in a way that few, if any, of its competitors have matched. The supercharger network is a particularly clear example of how this compounding advantage plays out. For years, it was viewed as a nice convenience for Tesla owners, nothing more. But as rival charging networks struggled with reliability, confusing payment systems, and inconsistent coverage, Tesla's network became reliable enough that competing automakers eventually began adopting Tesla's own charging standard just so their customers could use it. That's a remarkable position to be in. Rival brands now depend, at least in part, on infrastructure built and owned by the company they're trying to beat. None of this guarantees Tesla wins every future round of this competition. Chinese manufacturers, particularly BYD, have shown they can compete aggressively on price and scale, and the electric vehicle market is still young enough that a genuine surprise from any direction remains possible. Legacy automakers have deep resources, global manufacturing footprints, and decades of experience that shouldn't be dismissed. But the carbon-wrapped rotor is a useful symbol of something larger happening inside Tesla, a willingness to rebuild supposedly settled engineering problems from first principles rather than accepting the industry's inherited assumptions about what's achievable. What makes this motor worth paying attention to isn't just the horsepower figures or the efficiency gains, impressive as they are. It's what it represents about how Tesla approaches problems that everyone else had already decided were finished. The rest of the auto industry spent years optimizing around a limit that turned out not to be a real limit at all, just an assumption nobody had seriously challenged. Whether or not competitors managed to close this particular gap, the bigger lesson is uncomfortable for an entire industry built on decades of accumulated conventional wisdom. Sometimes the rules everyone agrees to follow are only rules until someone decides to test them.